All right, today we're going to talk about graphing exponential functions. First, a definition. An exponential function is a function whose equation can be put in the form y equals a times b to the x, where a is not 0, b has got to be greater than 0, and b can't be 1. All right, so the first question I think we should look at is, why are there restrictions on a and b? For example, why can't a be 0? Well, it's because if a is 0, then our equation becomes y equals 0 times b to the x, which is 0. 0 times anything is 0. So we don't really get anything interesting. We get a horizontal line. That's not very much fun. We have the same problem with b equals 1. If b equals 1, we have y equals a times 1 to the x. Well, 1 to the x is 1. So we get y equals a. Once again, we get a horizontal line. All right, so why does b have to be positive? Well, let's say b is a negative number. I'm going to pick negative 4 to the x. The problem we have with this is plugging in certain numbers. For example, if I were to put x equals 1/2, then y would be a times negative 4 to the 1/2. And we remember that a 1/2 power is the same as a square root. And the issue becomes, we get complex numbers. The square root of negative 4, we called that 2i earlier this year. We don't want to deal with complex numbers in this section. So that's why a can't be or b can't be negative. If b is negative, you quite often end up with complex numbers when you plug in values for x, and we don't want that. So we're going to use a to be not 0, b to be positive, and b can't be 1. All right, well, let's take a look at a graph of an exponential function. If we don't know much about a function and we want to draw its graph, probably the best thing to do is plug in some numbers and see what happens. So I'm going to plug in some positive numbers. I'm going to plug in 0. And I'm going to plug in some negative numbers. Let's start with 0. I always like to plug in 0 because when I plug in 0 for x, I always get my y-intercept. That'll be nice. Let's see, 3 to the 0, that's 1, and 1 times 2 is 2. Now let's go to the positive numbers because they're a little bit easier. When I plug in 1, 3 to the 1 is 3. 3 times 2 is 6. When I plug in 2, 3 squared is 9. 9 times 2 is 18. And finally, 3 cubed is 27. 27 times 2 is 54. All right, so notice what's happening. The y values get really big really fast. We went from 2 up to 54 already, and we've only gone, x has only gone up as high as 3. And if we did one more, we'd get 3 to the 4th, which is 81. Then we'd multiply by 2. We'd be in the 160s already. So that's something to see about exponential functions, is that the y values can grow really, really fast. All right, now let's plug in these negative numbers. When I plug in negative 1, I get 3 to the negative 1. I'm going to write this one down. 2 times 3 to the negative 1. Negative exponents, remember, those do not give negative answers. Rather, they make fractions. 3 to the negative 1 is a 3 down on bottom, so that's 2/3. Plug in negative 2, I get 2 times 3 to the negative 2. That's 2 over 3 squared, which is 2/9. All right, so now we're seeing a pattern, I hope. 2 times 3 to the negative 3. That's 2 over 3 cubed. That's 2 over 27. So now what's happening when we plug in these negative numbers, our y values are getting really, really small, but they're still positive, but they're getting close to 0. All right, so let's draw this. We have 0, 2. We have 1, 6. Right there. We have 2, 18, already way up off my scale. 354 would be way, way, way up here somewhere. I'm not even going to try to draw it. Negative 1, 2/3. Negative 2, 2/9. Negative 3, 2/27. So notice what's happening going in this direction. if I were to plug in -4, -5, -6, my denominator on my fraction would keep getting bigger. The top's always going to be the number 2. The bottom would keep getting bigger and bigger. When I take 2 and divide it by a bigger and bigger number, what's going to happen is my fractions are going to get smaller and smaller. They're going to get really, really close to 0, but they're never going to hit 0. My graph ends up looking something like this. All right, a few words we haven't used in a while. Domain. Domain means the x numbers. What kind of numbers could I plug in? Well, notice I had no issue plugging in positive numbers. I was able to plug in 0. I was able to plug in negative numbers. It looks like I can plug in all real numbers. The range, on the other hand, look at the y numbers that I got. I only got positive numbers. And that's going to happen. I'm never going to get 0. And I'm never going to get a negative number, because if I take 3 and raise it to a power, I might get a big number, or I might get a tiny little fraction, but it's never going to be 0 and it's never going to be negative. So my range is y is greater than 0. I only get positive numbers. And then we have something in an exponential function that we call an asymptote. And an asymptote means we're coming along and we're getting closer and closer and closer to a line. We're getting closer and closer and closer to the x-axis, but we never actually touch it because y never turns out to be the number 0. In that case, we say our asymptote is y equals 0, which means that's a line that our graph is getting really, really close to, but never touches. All right, let's try another graph here. Y equals 4 times 1/2 to the x. Again, I'm going to build a table. I'm going to plug in some numbers. Again, I really like plugging in 0 first, because when I plug in 0, that gives me my y-intercept. Plugging in 0 is pretty good because 1/2 to the 0, anything to the 0 is 1. 1 times 4 is 4. Plug in 1. If I plug in 1, I get 4 times 1/2. 4 times 1/2 is 2. Plug in 2, I get 4 times 1/2 squared. Well, 1/2 squared is 1/4. 4 times 1/4 is 1. And when I plug in 3, I get 4 times 1/2 cubed. 1/2 times 1/2 times 1/2 is 1/8. 4 times 1/8 turns out to be a half. So this time, notice what's happening. As I plug in positive numbers, my y numbers are getting smaller. Notice that's the opposite of what happened last time. When I plugged in positive numbers, my y numbers got really big. All right, now let's plug in some negative numbers. 4 times 1/2 to the negative 1, that's 4 times 2, which is 8. Because remember what a negative exponent does to a fraction. A negative exponent flips it, so the 2 comes up, the 1 goes down. 2 over 1 is 2. When I plug in negative 2, I get 4 times 1/2 to the negative 2. Again, remember what the negative is going to do is going to flip it. That's going to become a 2. So that's really 4 times 4 squared. The negative flips it, 2 over 1, and then the 2 is our exponent. 4 squared is 16. 16 times 4 is 64. So we see what's happening here. Our y numbers are getting really large really quickly here. 4 times 1/2 to the negative 3. That's 4 times 2 cubed. Oh, I made a mistake back here, didn't I? Sorry. This is 4 times 2 squared. I don't know why I changed that to a 4. When I flip that, that becomes a 2 over 1. Plus 2 squared. 2 squared is 4. 4 times 4. That one's only 16. Sorry about that. All right, this one I have written correctly. That's 2 cubed. That's 8. 8 times 4 is 32. All right, so we have 0, 4. I'm going to go this way this time. Negative 1, 8. Negative 2, 16. Well up off my graph already. Negative 3 would be way, way up here on the table. Can't draw that one. Let's see. 1, 2, that's here. 2, 1, that's there. And 3, 1/2. All right, so you see what's happening this time. We've got kind of the same shape, except it's flipped over the other way. And I missed a dot here, so you cheat and you make the dot bigger, you see. So, notice the difference in the two graphs. This one went upward, this one went downward. All right, let's answer the same questions again. Domain, again, I could plug in positive numbers. I could plug in negative numbers. I could plug in 0. So my domain is all real numbers again. My range, again, looking at the y numbers, notice I got positive numbers, positive numbers. I only got positive numbers. So my range is still y greater than 0. And my asymptote, again, this line, this is curve, it's coming down, and it's getting really, really close to the x-axis, but it's not touching it. So our asymptote is y equals 0. All right, so a few words you're going to hear. Y-intercept. Let's say we have y equals a times b to the x. Notice, for both of these problems, our y-intercept was 0, 2, and 2 happened to be the a number. For this one, our y-intercept was 0, 4, and 4 happens to be the a number. And that's always going to happen. When I plug in 0, b to the 0 is always going to be 1. 1 times a is going to be a. So my y-intercept is always going to be 0, comma a. Domain. For both of these problems, my domain was all reals. And that'll always happen with an exponential function. You can always plug in all the positive numbers, all the negative numbers, and 0. The range. You're only going to get positive answers. You won't get any negative answers with exponential functions. And our asymptote will be y equals 0. Growth and decay. This kind of graph we call exponential growth. As the x's get positive, it grows, and it grows very, very quickly. That happened because of the b number. In this case, the b number was 3, which happens to be bigger than 1. Whenever your b number is bigger than 1, you're going to get growth. So you will get growth when b is bigger than 1. And this one, we got what we call exponential decay. As our x numbers get bigger, our y numbers get very, very small. That's going to happen when b is a fraction less than 1. But of course, remember that b has to be positive. So there's our difference in growth and decay. We have growth when b is bigger than 1. We have decay when b is a fraction between 0 and 1. And then the last thing we talk about with exponential functions here is base multiplier. That's the b number. Look what happened here. To go from 2 to 6, you would multiply by 3, which is our base number. To go from 6 to 18, you would multiply by 3. To go from 18 to 54, you would multiply by 3. Conversely, going the other way, here, to go from 4 to 2, you would multiply by a half. To go from 2 to 1, you would again multiply by a half. So the base multiplier is always the number b. And we will see that this number b, this base multiplier thing, has a lot to do with when we have exponential functions and when we don't. Okay, so that's the first half of this section. There is going to be another video. So pause now, take a little break, and then come back in a few minutes and watch the other video.